Hello Internet, my name is Quinn and this is Blondihacks. Today I'm going to tackle a problem that's been plaguing me for some time, and that's fixturing conveniently and quickly on the rotary table. I've got a lot of little parts coming up in my near future to make on the rotary table, and my current fixturing setup has always been clunky, slow, and kind of annoying. So let's see what we can do about that. Rotary table setups are a lot of work, and let's talk about why. First of all, you have to get the x-axis of the table aligned with the x-axis of your mill so that 0 and 90 are x and y on the table. And that can be made quicker by making keys for the underside of the table. Rotary tables frequently have slots milled for you to do this. So I've done that, which makes that part quick. Then you got to get the center of the table aligned with the spindle on your mill. So for that, I made this mandrel. It's a Morse taper 2 because that's what this table has in the center of it. So I can put that in there, and that gives me a nice cylindrical reference in the center of the table. And I've also made these plugs that can go in that little pocket and help me align the table, because I can put one of these little pins in a collet in the spindle and drop it in there to get the spindle zeroed on the center of the table. And then I've also got some threads down the center of that mandrel, which can be used for light duty fixturing. Then those plugs that I showed you, some of the larger sizes, also have a hole in the middle, so I can use them for centering the spindle and for centering the part and for fixturing the part. These little buttons also have a shoulder on them the same thickness as my parallels, so then I can clamp the part down, and that suspends the part up above the table surface so that I can cut all the way around the part without touching the table. However, this table has an annoying property that the T-slots are aligned with the X and Y axis of the table, which is quite annoying because then when you've got a part clamped aligned with an axis like this, 3 of the T-slots are in useless places, and the 4th one is underneath the part. So this layout is really silly, honestly. I would want it to be like a typical drill press table where the T-slots are in an X pattern, because then when your part is aligned with an axis of the machine, as you would normally do, these T-slots are at an angle, and so they're always going to be in a good place to clamp, and the angle effectively gives you a variable distance to the part for your clamps to sit on, so you can always get just the right clamping distance. And because someone's going to say it, no, you can't change the orientation of the table relative to the markings on this rotary table. The markings are etched on the edge of the table. It's all one piece. These are all problems that I've been showing you that I hope to fix with my new fixture plate. I want the parts to be super quick and easy to clamp down with no need to suspend them above the table and all the fussiness that goes with that. So my thought is to make a sacrificial fixture plate that can sit on top of this table and be used for many, many years. I'll show you what I mean as we go along. The idea for a sacrificial fixture plate kind of came to me when I was doing the boiler for my Pennsylvania A3 switcher locomotive. I did a lot of tricky rotary table work using planed oak pieces as spoil boards. And this was super nice. Like, it was really nice just to be able to frankly wood screw down the parts, then cut with reckless abandon, not worrying about the surface of the table. So this was kind of my best ever rotary table experience, and I thought, well, what's a slightly classier version of this that I can build that will make every rotary experience this nice? Let's start by talking about T-nuts, because my new fixture plate is going to need to be attached to the rotary table with T-nuts. I've got one main set that I use with this table. You can see that they are the correct size, but they have a large thread in them that matches the strap clamp set for my mill. You'll note that I have the hole off-center on these T-nuts. I find that really useful for rotary tables because then you can get the T-nut right at the edge like this, and nothing is sticking out that's going to interfere with the locks or other things around the table. I want to use 1/4-20 hardware, however, so I'm going to make a new set of T-nuts for this table. I've needed a new set for this table for a long time anyway. I rarely use my full-size strap clamps on this table because it really isn't that big, so it's a good excuse to make some new T-nuts. If you've watched my Mill Skills playlist, then you watched me make T-nuts in a very fancy way, which was a pedagogical exercise to teach good machining fundamentals and not a fast way to make T-nuts. This that you're seeing is a fast way to make T-nuts if you just want T-nuts. A lot of commenters maybe didn't quite get what I was doing there, and I know it's a poor teacher who blames the student, but with YouTube comments, sometimes... Note that the threads are staked on the bottom so that bolts can't go all the way through these T-nuts, otherwise they turn into jacks and they start lifting up on the tops of the T-slots. You don't want that. So with 4 of those made now, I've got a nice easy way to clamp my fixture plate to the rotary table. Let's move on to the fixture plate itself. I ordered this very special piece of material for the purpose. I'm going to mount this on there, and that'll be my fixture plate. All right, great video, everyone. Thanks for coming along. I'm just kidding. Of course, we're not done. I want to figure out how big to make this thing and what shape to make it. I considered making it a little bigger than the table. I also considered making it square, but all those options would either interfere with the locks on the table and also would make it difficult for me to position the table close to my vise, which I often do. So I'm going to keep it round, and I'm going to keep it the same size as the rotary table itself. I'll start by laying out a rough circle that I'm going to cut out to shape on the bandsaw. The material that I'm using for this is called Mix 6. It's a free machining alloy of aluminum that's targeted at applications like this, fixture plates, jigs, and so on. And what's really nice about it compared to your standard 6061 is that it breaks chips. You'll see how amazing that is over on the lathe when we get there. But to start with, I'm going to cut this out on the bandsaw. And this is a really thick piece. It's 1.5 inches thick. And the reason that I did that is because, again, I want this plate to be sacrificial. So the idea is I don't have to worry about cutting into it like you would with the actual rotary table itself. And that makes setups on this thing extremely quick and convenient. It's not too difficult to set your cutter depth such that you're only cutting 5 or 10 thousandths into the substrate. So every 5 or 10 uses, as the top surface of it starts to get chewed up from the various cuts, I can just run a fly cutter over it in the mill and resurface it. Because it's 1.5 inches thick, I'll easily get 400 or 500 resurfacings out of it, which for how much I use the rotary table is almost certainly a lifetime supply of substrate material. I didn't want to go too much thicker than this because I don't want to add a whole lot of vertical height to my rotary table, so I settled on 1.5 inches. With that shape roughed in, I'm going to drill out a center hole through this thing that'll be used for subsequent operations. I'll do that on the drill press. I was confident that my float lock vise would be up to this task. It has no trouble clamping on large pieces like this. I am a fervent evangelist for float lock vices, as you probably know if you're a regular viewer. Now, the float lock vise itself was up to this challenge, no problem. However, my drill press table was not big enough to get the base clamp far enough away from the drill for a piece this big. So I couldn't get the drill centered because of the way it has to be clamped on the edge of the table. You might think I've finally found something that the float lock vise can't do, but oh no, the drill press table is just too small. The float lock vise has not failed me. I have failed the float lock vise. So fine, I'll strap clamp the piece down like some kind of chump. I'm going to do 2 different diameters here. I'm going to do a smooth bore through about the bottom third of the piece, and then a 1/4-20 thread for the top 2/3. So I'm starting with the smaller of those 2 sizes, and I'm going to go all the way through with that. And then I come in with the tap drill size for my thread, and I drill down about 2/3 of the way through the top to make the threads in the top. The idea is that I'll have a fixturing thread for the lathe, but then I'll also have a reference diameter, because threads aren't a very good concentric reference for turning parts. To tap that thread, I would normally use my spring-loaded tap follower here, but that requires moving the table down, and this is a round column machine, so I lose my XY position if I do that. Instead, I'll cheat and put the tap in the Jacob's chuck and use that to tap this thread. If you're a regular viewer, you know this is something that I generally recommend against, and I'm actually going to be talking a lot more about this type of tapping here in this video, so stay tuned. But for now, just know that I'm feeling a little bit dirty doing this, but it got the job done. To turn the OD of that big slab, I'm going to make a mandrel to hold it in the lathe. I've got a fairly large diameter piece of some junk steel, and I'm going to turn down that 1/4-20 thread. And the reason I'm starting with such a large piece is because I want a large surface area of shoulder behind the mandrel. Because the diameter of the disc that I'm turning is so large, I want lots of square reference and support behind the mandrel. The threaded hole in the center is quite small, but I still want a decent amount of surface area backing up the piece that I'm turning. So it does mean I have to turn down quite a bit of material to get this large diameter round bar all the way down to a 1/4-20 thread, but I think it'll work in the end. I also put a center in it because my idea was that the mandrel will stick all the way through the disc, and then I'll have tail support on the far side of it. Of course, halfway through this operation, I forgot that was the plan, and I made this mandrel too short. But we'll recover from that in a minute. Here you can see me taking a light facing cut on the back of that mandrel surface just to make sure that's nice and square to back up the disc. Then I turned a small diameter right on the end that's going to fit into that smooth bore that I mentioned is in the bottom third of that aluminum plate. Then the upper 2/3 gets the thread cut into it, and this is what's actually going to hold the piece. I went with a threaded mandrel for this rather than a smooth mandrel with a thread and a nut on the end, which would be more concentric. Because this is a very large diameter piece, and not a very beefy mandrel. So by making it a threaded mandrel, that's going to guarantee that I've got enough holding force on that piece. Because of the large diameter, the cutting forces are going to have a lot of leverage on the mandrel. If I was relying on the friction of a nut on the front surface to hold this thing against those cutting forces, I'm not convinced that would work. And this is where I realized I'd forgotten to make the mandrel long enough to stick through for tail support. So instead I decided I'll just cut a center in the aluminum itself and use this for tail support. This is going to be the underside of this fixture plate, and a center cut here is not going to hurt anything. It won't be perfectly concentric because the concentricity of the tailstock will be set by where the aluminum happens to be sitting on those threads, which is probably not exactly perfect. And in fact, if you look really closely in the upcoming turning footage, you will see the tailstock wobbling ever so slightly because it's not perfectly concentric with the material that's sitting on the threads due to the clearances in the threads themselves. That's why threads don't make a great concentricity reference. Next up is the obligatory compound slide dance that one has to do when turning large diameter pieces on a small lathe. These machines never have quite enough travel on the cross slide to get far enough away from large diameter parts. Thus, some jiggery-pokery with compound slide and tool post angle is always required to get the reach outboard that you need. Usually involves angling the compound slide away from the work a little bit to get extra reach. The problem I did not anticipate was that I ran out of compound slide travel before I could get to the far edge of the part. Because the part is too large a diameter to clear my cross slide, I'm within the swing of the lathe, but not within the swing of the cross slide. There's a little fine print thing they never tell you in the brochures for your lathe. However, I think I can get away with this. I can do this in sections. The area that is in the way above the cross slide, I can turn that down first because the final diameter of the part will clear the cross slide. Thus, if I turn the first 2/3 down almost to final diameter, then I can get the cross slide under that section of the part and turn down the back third and then do some final cuts on the whole thing. Now comes the cool part. Look how nicely this aluminum is turning. If you've done any amount of turning of 6061 aluminum on a lathe, you know that it does not break chips. I don't care what tool grind you've got or what profiles you've got or what fancy carbide insert you've got. It makes giant stringy chips that are just an absolute nightmare and is why I absolutely hate aluminum on the lathe. However, this stuff is breaking chips like crazy. It breaks chips like free machining steel. It is so nice. This Mix 6 is so nice you will never buy 6061 again. Surface finish comes out great. It makes chips like a champ. Metric horns of victory all the way around. Love this stuff. And now, as you can see, we clear the cross slide, barely. Clearance is clearance, clearance. And now I can reach that last little strip at the back and turn that down. Then one final finishing cut all the way across the entire thing now that it will all clear the cross slide. I did end up reducing the overall diameter of the part just slightly. My design diameter didn't quite clear the cross slide. So I went down about 100 thousandths to make it clear, and yeah, all's well that ends well. That came out really, really nice. Very happy with that. That was a lot of material to remove, and now my lathe looks like an aluminum Superfund site, so I'm going to go ahead and clean this up before moving on. Next, I checked the parallelism of the top and bottom surfaces, because of course we want them to be parallel so that parts sitting on this are going to be parallel to the top of the rotary table. I was expecting to need to have to turn these surfaces to get them parallel, but shockingly the whole thing is within 1,000th of perfectly parallel. That surprised me because I did not specifically order tight tolerance material. If you take a close look at the virgin material, you see those circular marks on it? Those actually look like Blanchard grinding marks, which is what you get if you order precision tight tolerance material that's designed for making gauge plates and that sort of thing. So it may be that the piece I ordered, they cut it from a piece of tight tolerance because that happened to be what they had lying around in their offcuts for such a small piece. Or it could be that McMaster Carr has a really, really good cold saw. I don't know. Those could be cold saw marks. But however it happened, I ended up with a piece of material that was extremely parallel. And that was an amazing gift because it saves me a lot of work. That means that the last thing I have to do on the lathe is turn this all the way down to a little boss on the bottom that's going to register in that Morse taper mandrel that I showed you earlier. That's going to make this fixture plate self-centering on the rotary table itself. Again, just to make setup and installation of this thing super quick and super easy. I like rotary tables, they're neat and they're a lot of fun, but the truth is for most operations, they're usually the last choice. There's pretty much always an easier way to do your operation, with the exception of certain things like blind curved slots, for example, that really can't be done any other way on a manual milling machine. But if I can make the rotary table easy enough to set up and use, then I might be more inclined to use it more often. After roughing that in most of the way, then I can get the tailstock out of the way so that I can get a better angle on my insert and finish turning down the boss all the way down to close to the final diameter with a few aggressive facing cuts, and then I'll turn my tool around and make a couple of finishing cuts to get the diameter just perfect. This needs to be an extremely accurate fit in that mandrel, so I gotta take my time and get this accurate. For the last couple of finishing cuts, I actually switched to high-speed steel because I couldn't get the carbide insert to take fine enough cuts anymore. Carbide is great, but it's not super happy about making very, very fine cuts when you're trying to take off that last like half or 1/1000th to get a perfect fit on something. High-speed steel, still the way to go. And finally, I take a file and break all of those edges. I also put somewhat of a chamfer on what will become the top surface, just so that it's more pleasant to handle the table and be around it. And of course, because chamfers are what separate us from the animals. That's of course extremely tight on there now, because the cutting forces just serve to tighten it because of that threaded mandrel, but that's good. That was working as designed. But now I can get it off of there because we are done with the lathe work for this part. It's going to be over to the milling machine next to drill all the holes in it. A quick test fit on the rotary table first to make sure I got that boss the right diameter. Should slip in there easily, but have no play in it at all. And ooh, mission accomplished. That's beautiful. No movement in that at all, and it's easy to slip in and out. I love it. That's going to be very repeatable, which I love. So I set the whole thing up on the mill now, and I'm going to clamp the fixture plate in place on top of the rotary table. I'm going to put the mounting bolts in it first. This I did just by putting the desired bolt in the mill and just kind of lining it up to a place where it looked not too close to the edges, but was also on a round number on the DRO to make it easy to figure out where to put everything for all four corners, and I won't make any mistakes. Start by drilling through clearance for these bolts, and then I hold the T-nut up with the short bolts installed, and I bring my counterboring drill down to where it needs to finish to get these bolts to sit in the right place. I want these bolts to be as short as practical, because again, this is going to get resurfaced over the years, so over the years, the top surface of this table is going to be moving downwards, and I want to get as many resurfacings as I can before I encounter the tops of these mounting bolts. For these really deep counterbores, I'm using DeWalt Pilot Point drills. They have a square grind on them, which is a really trick tool for doing this kind of thing. Makes a really deep counterbore easy to do. Quick test fit with that to make sure that I did that right. And that is looking really good. That will now bolt itself down. I did the other three corners the same way, and then I bolt this thing down using the mounting bolts, and I can remove the strap clamps for all the rest of the operations. Next, I need to figure out what hole pattern I want for this thing. My first instinct was to go with a radial pattern like this, which would sort of mimic like the T-slots on a drill press. However, it creates issues where you've got too much density of holes in the center where you don't really need them, and very little density around the outer edges, which is kind of where you want more density. You could do some sort of a hierarchical thing with multiple different radii of radial patterns, but then that gets really complicated on the DRO because I have to be able to do multiple operations on every hole in an easy and not error-prone way. So then I also mocked up a grid pattern to see what that would look like, and I like the grid pattern a lot more. I would go a little less dense than this, but you can see that it's going to give me holes pretty much anywhere I might want, and this is a very simple and easy pattern to do, which makes me 48% less likely to bork it up. I want to use the same little strap clamp hardware that came with this Dayton CNC Products fixture plate. It's 1/4-20 hardware, and it has these really nice little clamps that come with it. I also did consider that little grouping pattern that it has for the threaded holes, which is very nice, but would be a ton of extra work. So I decided to stick with just a plain grid. I started by center drilling all of those positions. Then I find the depth for my tapping drill size. I want it to go most of the way through the plate, but not all the way through, of course, so I don't touch the rotary table underneath. So these will all be blind holes. These get all drilled out to depth. This is a lot of holes to do, which is why I wanted to keep it simple pattern-wise to make sure I don't screw it up. One thing that's interesting, when you're doing a lot of an operation, even a simple one like drilling holes, you get better at it. And after 5 or 10 holes, I had really gotten the feel for the perfect feed rate on this drill, and I got to the point where I could feed quite quickly, and the chips wouldn't pack up in the hole, and I wouldn't have to do a lot of peck drilling, And it just was surprising how much quicker I got at even such a simple operation. The human brain is really an amazing thing. Well, some of them are more amazing than others, but you get it. Okay, but drilling is easy. I'll get all those cleared out for the part that could be really miserable, and that's the tapping. Well, let's talk about tapping, because this is a perfect use case for power tapping, which is not something you've seen me do on this channel because I don't do a lot of it. This is a humble hand tap. You cannot throw a rock on YouTube without hitting 6 people that put these in their power drills and power tap with them. This is a machine tap. It is specifically engineered for power tapping. Specifically, it breaks its own chips and it clears its own chips, neither of which hand taps can do. That's why you're not really supposed to power tap with hand taps. But so many people do it, so it must be okay, right? Well, machining isn't really about right or wrong, correct or incorrect. It's about understanding the trade-offs of the decisions that you're making so that you can do things one way or another, whatever works for you, as long as you understand the pros and cons of what you're doing, and if it goes wrong, then you'll know why. In the case of tapping, the reason you don't want to power tap with hand taps is because they can't break or clear their own chips. So as that tap runs in, it's just getting more and more jammed up. That's why when you hand tap, you have to back out the tap periodically to break the chip and clear chips as you go down. Now, that doesn't mean that it never works to put a hand tap in a cordless drill. See YouTube. But on smaller tap sizes, when those chips jam up in that hole, you will break that tap in that hole, and now you're having a real bad day. Furthermore, taps are extremely hard. They're among the hardest steels in your shop, as are Jacob chuck jaws. They are also extremely hard because drill shanks are fairly soft. So what that means is, tap in a Jacob's chuck is like holding glass with glass. You do not have a good grip on that. And that can be a pro or con, as you'll see, but what it means is on larger tap sizes, if you put them in your cordless drill, that tap is just going to slip and it's not going to work very well. And that's also a little bit abusive on your Jacob's chuck jaws, but that's probably not the end of the world. The point of this speech, before I fall off of this high horse and hurt myself, is not to tell you shouldn't ever do what you see other people doing with hand taps. It's just understand what you're doing, and if it works for you, great. I'm not going to tell you not to. It's your shop, but at least understand the things that you're playing with and why it works or doesn't. There are other tap geometries, such as this fellow. This is a spiral point tap, and they can break their own chips, but they're still not great at clearing them. So these work okay for power tapping in a through hole, and they're also really nice hand taps, but still not a great choice for a blind hole. Assuming then that I've hopefully convinced you that machine taps are a good idea for power tapping, what's the right way to use them in the machine? Well, the ideal way to use them is with a tapping head. Now, I happen to have one of these. This was an amazing donation by the fine folks at the Hamilton Model Engineering Club. However, the largest tap holder that it has is still too small for this tap. This is a small tapping head designed for very small taps. Instead, I'm going to do something that extremely recently I've told you not to do. I'm going to put it in my Jacob's chuck. That high horse I mentioned is named Hypocrisy, and he's a lovely boy. Now, aside from the somewhat abusiveness of the Jacob's chuck that I mentioned, power tapping with the Jacob's chuck is actually not a terrible idea if you're using the right tap, because if the torque gets too high, then the tap is just going to slip in the jaws and help keep that tap from breaking. Like I said, no absolute rights or wrongs in the machine shop, just different trade-offs. I tested this setup in an offcut of the same material to get my speeds and feeds down, and it worked extremely well, so I'm ready to go for the real thing. About 110 RPM worked really well. I've got my depth marked. That's the point where that tap is going to jam up and probably break, because these are blind holes, so I want to stop short of that. But as you can see, I just let that tap roll in, and it pulls the quill down on its own accord, and then I stop it and reverse the mill when it gets to the desired depth, and out it comes. With the right tap, this goes very smoothly, very low drama, and very quickly. That worked beautifully. Since I have 30-something of these holes to do, this is going to save me a lot of effort. Here's a wider shot so you can see what it looks like from the operator. I do have my hand on the quill occasionally, but I'm just kind of babying it a little bit, making sure it doesn't get stuck and keeping it from snapping back when it pops out of that hole again. This setup worked really well. It was definitely the right way to do this. Hand tapping all of these would have been a nightmare. I want these all fully tapped all the way to depth because, again, I'm going to be resurfacing this plate. So as I lower the top surface, I'm just going to be shortening the threads and automatically refreshing those as well as the table surface drops. And occasionally, the tap would get stuck, as you'll see here, especially at the bottom. Might get a little jammed up with some chips. And what will happen then is that Jacob's chuck will slip, and it'll pop out of the jaws like that. So in a case like this, I just put the tap wrench on it and back it out a little bit to unstick it, like so. And then I can put the chuck back on, retighten that, and power the mill back out again. Again, for occasional use, this is fine. If I was going to do a lot of this, I'd get a proper tapping head. I wouldn't want to abuse my Jacob's chuck this way for a whole bunch of uses, but, you know, for one fixture plate here and there, it's just fine. Since I'm all set up like this, I might as well chamfer these holes with a chamfering tool as well. I normally chamfer by hand, but machine chamfers do look nicer, and I've got all the DRO coordinates in my head already, so might as well knock them out nicely like this. Of course, after a couple of resurfacings, I'll lose these chamfers and have to redo them anyway, but that's okay. It'll look nice for some YouTube photography. You may have noticed that I didn't create any kind of centering reference in the center of the table like those little plugs that I had in my previous setup. I consciously decided not to do that because I'm going to use this fixture plate for a lot of very small parts, and I didn't want to have a big clunky recess in the middle of the table because of that. So what I've decided is that I'll be using the spindle of the mill and pins in the spindle to center the pieces, and then I'll clamp them down in situ and retract the quill. That's my plan for getting the bores that I'm going to be creating centered on the rotary table. We'll see how that works out. I can always add that reference for those little plugs if I want to later, but for now I like the smoothness of the top as it is. Here's a quick example of what the fixture plate looks like in use. Making some locomotive parts, which you've already seen if you watch all of my videos, and it actually worked out great. This was the first official use. You can see the quote-unquote damage left in the plate by this. I'll easily have another half dozen parts at least out of this before I need to resurface it. And then between parts, I can just do a quick stoning with precision ground flat stones to remove any burrs that would create high spots that would interfere with the reference of the flat surface. That is it for this project. I'm excited to give this thing a whirl, and I'll let you know how it works out. It's just an idea that I had. I don't know for sure it's going to be perfect. Maybe I'll have to make some adjustments, but if I do, I'll let you know. Thank you so much for watching. Thanks to my patrons for making all of this content possible, and I will see you next time.